Okay, welcome back. This is lecture 12. In this lecture we'll be talking about orthogonal and orthonormal basis. So what do these terms mean? Okay, they are what they sound like. Okay, so if we have a subspace W and it has some basis B, some set of vectors B, then if B happens to be an orthogonal set of vectors, then B is called an orthogonal basis for W. Okay. Also, if B is an orthonormal set of vectors, then B is an orthonormal basis for W. Okay, so an easy example of an orthonormal basis is the standard basis for Rn. Okay, and also just by definition, every orthonormal basis is also orthogonal. Right? Okay, so let's look at this familiar example. Okay, let A1 be 1, 1, 0 and A2 be 0, 1, 1. So these two vectors are a basis for W, where W is the span of those two vectors. Okay, but A1 and A2 are not an orthogonal basis, right? Because if we take the dot product of A1 and A2, we get 1, which isn't 0. Okay, so this is our question. Can we transform A1, A2 into an orthogonal set? In other words, can we take this basis and make it into an orthogonal basis for W? The answer is yes, by taking some projections. Okay, so the idea is I'm going to keep the first vector, A1, the same. Okay, I'm not going to change that one, but I'm going to replace A2 with a vector that's orthogonal to A1. Okay, so we know how to do this via projections, right? So here's A1, right? And here's A2, right? I want a vector that's orthogonal to A1. Okay, so if this line is the span of A1, then I want a vector that's in the orthogonal complement of the span of A1. In other words, a vector in this space. So we know that when we take the projection of A2 onto A1, we get that vector. Well, we get a vector that's the projection of A2 inside the span, but we also get this other vector, right? What we were calling the B hat before, which lives inside the orthogonal complement of the space you're projecting it onto, right? And if we look at the right angle triangle, right, this is the formula for this vector here that's orthogonal to A1. Okay, A2 minus the projection. Okay, so this vector, A2 minus the projection of A2 onto A1, is orthogonal to A1. Okay, so if I work this out for our example here, I'll get that this vector here, okay, is going to equal this. Okay, and that's the vector I'm going to replace A2 with. Okay, I'm going to call it V2. Okay, and I'm going to leave U1 the same, but now I'm just going to relabel it to V1. Okay, so now V1 and V2 are an orthogonal set, right? You can check the dot product is 0 now. Okay, so we've created V2 from A2 by sort of, taking A2 and just prying it so that it's forcing it to be orthogonal to A1. Okay, so we did something to it, right? So a question is, how do we know that the span of the original vectors, a1 and a2, is equal to the span of the new vectors, the orthogonal vectors, v1 and v2, right? I'm looking for a basis for w, right? How do I know that when I transformed a2 into v2, somehow that didn't spoil the span, didn't change the span, right? The span of v1 and v2, right, they're independent, is going to be a plane, right? How do we know it's the same plane as the original plane is the question, okay? So here's the answer, okay? Note that v2 was calculated like this, right? a2 minus the projection, which we can write like this. So if we look at this, this part here is just a number. a1 is a vector, a2 is a vector. So v2 is a linear combination of a1 and a2, right? You can also say that v2 is in the span of a1 and a2. Okay. We also know v1 is also in the span of a1 and a2, right? Just because v1 is a1. Okay. So what do we know in total? Okay. So W is the span of A1 and A2. It's a two-dimensional space. V1 and V2 are two independent vectors inside of W. Okay. Therefore, we can conclude that the span of V1 and V2 is equal to W. Why can we say that? It's a consequence of the basis theorem from lecture 7, right? If you have a two-dimensional space, then any two independent vectors in that space will automatically be a basis and therefore automatically span that space. Okay, so this procedure will not ruin the span of the vectors. It will retain the span, which is what we want. Okay, so we can conclude that V1, V2 is an orthogonal basis for W. Okay, well, we can go a step farther, right? We can turn this into an orthonormal basis pretty easily, right? Okay, so I have V1, V2. I'm going to transform it into U1, U2 just by normalizing V1 and normalizing V2. Okay, so remember, this is how we normalize the vectors. We divide by their length. Okay, and this is the result here. So U1, U2 is an orthonormal basis for W. Okay, so in our example, we took two independent vectors and using projections, we transformed it into two orthonormal vectors. Okay. So you can ask, does that procedure work for more vectors? Okay. The answer is yes. Okay. You can do it for as many vectors as you like. Okay. So the procedure, which is just an extension of what we just did, is called the Gram-Schmidt process or procedure. Okay, it transforms an independent set of vectors into an orthogonal set that spans the same space as the original set of vectors. Okay, so this is the procedure. Okay, so your input is a basis or a set of independent vectors. So they're calling them the H's, sorry, the X's. Okay, the first vector v1 you just set to be the first x like we did before. Okay, v2 is going to be the procedure we did before, right? We take x2 and subtract off the projection of x2 onto v1. Okay, so that's what this formula is saying here, right? It's saying this expression is equal to the projection of x2 onto v1. And then for the third step, we want a vector that's orthogonal to the first two vectors. In other words, we want to compute a vector that's in the orthogonal complement of the span of the first two vectors. Okay? And you do that by taking x3 and subtracting off the projection of x3 onto the first vector and subtracting off the projection of x3 onto the second vector. Okay, so just keep on doing this, and in the end you'll have v1 through vp that span the same space as the original vectors. Okay. Okay, so notice now what we're able to do with any basis for a subspace W. Okay, so if we have a basis for the subspace W, okay, if it's not orthogonal, then we can transform it into an orthogonal basis for W using the Gram-Schmidt process we just went over. Right? We can always do that. And then we can further normalize that set of basis vectors into an orthonormal basis, right? That's even easier than the Gram-Schmidt, right? You're just dividing by the length of each vector. Okay, so what can we say in the end? Okay, so every non-zero subspace W has a basis, okay? And since we can always do this procedure, we can always create an orthonormal basis for W. Okay? Another thing to observe is that for a basis, we require these vectors to be independent, right? So we can think of orthogonality as an upgraded version of independence. Okay, so remember, to be independent, let's say for two vectors, they need to point in different directions. Right? So if you have this vector, and then you have this vector, right? That's good enough to be independent since they point in different directions. Okay, so orthogonality is sort of the most extreme form of independence. Okay, so not only do we require that the vectors point in different directions, right? We require they point in completely different directions, right? In perpendicular directions. Okay, so in that sense, orthogonality is a stronger form of independence. Okay, so you may ask, why do we desire orthogonality and orthonormality so much? Well, we'll do a few examples of how orthogonality will help us with some of our computations now. Okay, so recall from lecture 11, the previous lecture, we had this theorem. Okay, if you had q many vectors, okay, and you consider the space, the subspace W, which is the span of those vectors, okay, if you wanted to compute a projection matrix, which would project any vector in any vector B in Rn onto the subspace, okay, you would compute this projection matrix using this formula here. Okay, and you may remember that it can be a bit of work to multiply this, then compute the inverse, and then multiply it all out. Okay, so if the vectors are orthogonal, okay, so not just independent, orthogonal, then we have a simplification of this formula, okay, which we'll go through now. Okay, so let's suppose instead that A1 through AQ is an orthonormal set of vectors. Okay, not just independent, orthonormal. Okay, what does P, the projection matrix, look like then? Okay, so I'm going to use this formula again. Okay, so let's concentrate on the middle part here. A transpose times A. Okay, what is that going to look like if the A's are orthonormal? Okay, so write A transpose like this, write A like this, okay, and A transpose times A is going to look like this, right? A bunch of dot products between the A's, right, in this formation, okay? So, since the A's are orthonormal, whenever we're taking the dot product of AI times AJ, it's going to be 0 if I is not J. Right? That's just the definition of an orthogonal set. Okay, so what does that mean for this matrix? Right? It means this is going to be 0, this is going to be 0, these are going to be 0, this. Everything not on the diagonal is going to be 0. Okay. Also, if we're looking at AI times or dot AJ, if I equals J, okay, so the stuff on the diagonal, the dot product is going to be 1, right? Since all the A's are normal vectors, the length is 1, and that means when you take the dot product with itself, it's also 1. So, what does that mean? That means that A transpose A is the identity matrix, right? A Q by Q identity matrix. Okay, so that greatly simplifies this, right? A transpose A is the identity, so the inverse is also the identity, right? So we get that P is equal to A times the identity times A transpose, so this whole part in the middle just drops out, right? And we get that the projection matrix is equal to A times A transpose. Okay, so when A has orthonormal columns, the related projection matrix is A times A transpose. Okay, so what does that mean for the formula for projecting a B onto W? Okay, let's work out what that implies for a formula for this. Okay, so projection of B onto W is equal to the matrix P, this guy, times B. So we write it like this, A times A transpose times B. Okay, so let's remember what these matrices are. This is what A looks like, this is what A transpose looks like, and B is just an n by 1 vector. Okay, so let's multiply this part first. Okay, so this is just a matrix times a vector. Okay, so I'm going to use the dot product rule to compute this because it's the rows that are known here. So it's easier to use the dot product rule, right? So it's going to be A1 dot B for the first entry, and so on. So it looks like this. Okay, so A transpose times B is going to be a Q by 1 vector. Okay, now we still have to multiply it by A, right? Okay, so now I'm going to use the column rule for multiplying A times a vector, because why? Because we have columns over here, and so it's easier to think of it like that, right? So how does this work? We take A1 dot B, so this is just a number, many columns of A1, okay, we take A2 dot B, many copies of A2, okay, and so on, right? And then when we sum it up, it's going to be an n by 1 vector, okay? So, conclusion, when the A's are orthonormal, okay, computing the projection onto W is greatly simplified, right? Instead of computing this, where we have to compute this product and then compute the inverse and then compute 2 more products, all we have to do is take a few dot products and then add them up. This is computationally much simpler than the above method, right, when we don't have orthogonality. Okay, so this summarizes what we just did as a theorem. Okay, so let the vectors A1 through AQ be orthonormal and write the matrix A. Okay, so the projection matrix simplifies to A times A transpose. Okay, and further, we can get an explicit formula like this that tells us how to compute the projection of B onto the subspace W, which is a column space of A. Okay. So let's make a few observations here. So let's look at the formula we got here, right? So since our A's are orthonormal, AI dot AI is equal to 1. Okay, so for each of these, right, it's equal to the expression we have up here, and then divided by AI dot AI, since this is just equal to 1, right? So this and this are the same expression, right? But what is this here? This is just the projection of B onto AI. Okay, so each one of these is the projection of B onto AI. Okay, so to project onto a subspace with orthonormal basis, what we're doing is projecting onto each one of the basis elements and just adding it up. Okay, so we can write this formula as projections like this instead. Okay, and I'll also note that if the AIs are orthogonal but not orthonormal, you can use this equation and it will work. Okay, you can't use this equation, but you can use this equation. Okay, now I'll highlight another way in which orthogonal basis will save us work. Okay, so remember the coordinates relative to a basis. Okay, so let B be a basis for Rn. Okay, then for x in Rn, we can write x as a linear combination of the basis elements. Okay, and the weights, or the coordinates, the CIs, those will be unique. Okay, and then we call this xb the b coordinate vector, which just has the weights C1 through Cn, which satisfy this equation. Okay, and so how do we solve for that? Okay, so it's a fair bit of work to solve for it. Okay, so we write the matrix P with the A's as columns. Okay, so there's two sort of ways to solve for it. We can write this matrix, or write this equation, and then solve it by multiplying both sides on the left by P inverse. Okay, so this involves computing the inverse of P. Okay, so there's some work there. We can also do it this way, where we write P an X in an augmented matrix and then put it into reduced row echelon form. Also quite a bit of work. Okay, so you probably guess what I'm getting at is that now assume that B is not just a basis, but an orthonormal basis. Okay, so that's what we're going to do now. Okay. So assume that we have a basis, and it's an orthonormal basis for Rn. Okay, so in this case, what is the projection matrix? Okay, so the projection matrix is going to be this. A transpose times A inverse. We know that's going to be the identity. Okay, and then A times A transpose. Okay, but since A, or the A's are orthonormal, the matrix A is going to be an orthogonal matrix, right? In this case, A will be an n by n matrix, right? And it will be orthogonal because all its columns are orthonormal. So we're just left with A times A transpose, and we know for orthogonal matrices, that equals the identity. Okay, so W is, the space W, which we're projecting onto, what is it? It's the column space of A, okay? And in this case, it's going to be all of Rn, right? Because we have n many independent vectors. Okay, so this is a bit strange, right? Before we were projecting onto subspaces, like smaller subspaces in Rn, right? Now we're projecting onto the entire space. Okay, so what does that mean? Well, it still makes sense. Okay, so if you have an X in Rn, then what does it mean to project X onto Rn? It just gives you the same vector again, X, right? So P being the identity matrix makes sense in this case. Projecting any vector in Rn onto Rn is just Rn again, is just X again. Okay. And that's summarized by this. Okay, so what was the point of doing that? Well, from the previous theorem, we know that the projection of X onto Rn has this form, right? By the previous theorem, since the A's are orthonormal, right? And we just said up here that the projection of X onto Rn is equal to X. Okay, so that means that this expression here is also equal to X. Okay, so if X equals this, and this is the sort of X we're looking for when coordinating, when computing the B coordinate, then this expression tells us what the coordinates are, right? These guys are the coordinates. The dot products in front of the vectors are going to be the C's of the B coordinate when B is an orthonormal basis, right? Okay, so in other words, we can compute XB as this, right? Compute the C's, the coordinates relative to B, just take the dot product of X with each of the orthogonal or orthonormal bases. So this is much simpler than inverting a matrix and multiplying it, and it's much simpler than computing the reduced row echelon form of this larger augmented matrix. Okay, so having an orthonormal basis makes computations like this much simpler. Okay, and as a side note, if B is just orthogonal but not orthonormal, okay, then we still get a good simplification. Okay, it just looks like this instead. Okay, and you can verify this with the previous section. Okay. Okay, so now we'll talk about a factorization we get out of projections and the Gram-Schmidt process. So suppose we have a matrix A which has q many independent columns. So we can apply the Gram-Schmidt process to the A's to get an orthogonal set, we'll call it V's, which can then be normalized into an orthonormal set, call it U's. Now I form a matrix Q out of that orthonormal set. Okay. So now we observe that since the U's and the the A's are related, okay, there should be a matrix which connects these two A and Q matrices. Okay, so there should be some matrix R which satisfies this. Okay, and of course there is. Okay, and this is the form of that matrix. Okay, so this is R. Okay, and what it is all the dot products between the U's and the A's. Okay, and they're a more concise way to define R is like this. Okay, all the dot products between the U's and the A's in this formation. Okay, so a lot of these dot products are going to end up being 0. Okay, just by the way the Gram-Schmidt procedure works. Okay, so remember how it works is starts with the first vector and it keeps it the same. Then it constructs the second vector, which it makes sure is orthogonal to the first vector. Then it constructs the third vector, which it makes sure is orthogonal to the first two vectors, and so on. Okay, so a vector is orthogonal to the ones that come before it, but it's not necessarily orthogonal to the ones that come after it. Okay, and we have two sets of vectors going on here, ui and aj. Okay, so here's the criteria to check which pairs of u's and a's will be 0. Okay, and it works out that if you have ui dot aj, they will be orthogonal when I is greater than j. Okay, and the consequence for our matrix R is that it's going to be upper triangular. You're going to get zeros everywhere below the main diagonal, like this. Okay, and this R is going to complete our factorization. Okay, A times QR is going to be true. Okay, so this is the theorem which states the QR factorization. Okay, so if we let A be a matrix with Q many independent columns, and we let Q be the matrix that has columns where we've orthonormalized the A's using the Gram-Schmidt procedure. Okay, and if we define R as we did before using these dot products, okay, then R is an invertible upper triangular matrix and A equals QR. Okay, so this is another way we can factorize a matrix. Okay, so notice it only applies for special A's, right? It needs to have independent columns. But whenever you can write a matrix as a product of an invertible matrix and a product of a matrix with orthonormal columns, Q and R are more manageable and understandable than A on its own. So there can be computational advantages for factoring A like this. Okay, so let's just see a quick example of a QR factorization. Okay, so we're going to use this familiar example. Okay, so we let this be A with our A1 and A2. And earlier we computed orthonormal versions of A1 and A2. Computed it to be this. Okay, and then that means that we get a QR factorization of A like this. A times Q, right, where we just set Q to have these columns, and R, where these are the appropriate dot products. Okay, and notice it is upper triangular.